is, yeah, I did forgot to put this picture in there. But in 151 we had the pictures, but this just shows what the orbitals look like. So the S is a sphere, the P is the figure 8, and the reason there's 3 possibilities, and we're going to walk through it. Actually, let's go through these notes and then I'll bring that up. So this is partial review, and to make sure to help you to fully grasp it, what we're looking at is where the electron is in the atom. And there's Niels Bohr. This is one of the most wonderful quotes that if you think you understand this, then you definitely don't. So, right, so those who are not shocked when they come across the quantum theory, you can't possibly understand it, because, so ponder that with anything. All right, so the shell is given that designation N. It's called the principal quantum number, and N tells us what?
The number of the orbitals. Is that right?
Not quite. N is telling us
Size of the orbital.
the size of the orbital. So how far, size of the orbital, or how far out you are, what layer. And N is a whole number. So N is 1, 2, 3, 4, etc. So it's saying which layer are we, which floor. I often talk about this as like it's an apartment building. So are we on the first floor, the second floor, the third floor? In our classroom, it's actually wonderful because it's a stadium classroom. So there's 5 levels. And so it works beautifully for this lecture. It also tells you as you increase N, you increase the distance from the nucleus. So which level you're at. So are you on floor 1, 2, 3, 4, 5? Distance from the nucleus. We just did a whole bunch with this in this study set. So if you did do the study set, then you should be ready to embrace this. And if you had trouble with the study set, then hopefully this will help fill in some of that. It also, as you increase N, you increase the energy. So if you reside on the 5th level, you have a lot higher energy than at the 1st level. And so electrons always exist at the lowest level possible, but there is a maximum occupancy at each level. And we're going to get into that when we get through this page. All right, the subshell is L. And what does L tell us about the orbital? So you were right, Major. This is all talking about the orbital. Which, by the way, the orbital is the pathway or the path of the electron, which is a lovely way of saying it. Remember, electrons, you can think of them as running around the track like a little bunny rabbit, but they're really pulses. We talk about them as waves, but a better way to think of it is the type of waves we're talking about are pulsing waves. So if you throw a rock into a puddle or into a pond, you see waves come out, but they look like pulses one after the other. And that's what these are. But they can only be at certain levels. They're not like continually expanding like they are when you drop the pebble into the water. L tells us the
shape of the orbital.
The shape of the orbital, yes. And it does that because what L is actually giving you is the number of nodes. And so they designated them. I don't know who designated them SPDF. In Schrodinger's original formula, if L was called 0, 1, 2, or 3. I should put the mask on. There we go. It doesn't last long. It's, yeah. It's lopsided. My head must be lopsided. I can't see out of it. All right. You know, Captain America does not have very good vision. He should get his eyes checked. Yeah, so the L number is the number of nodes, is what that's actually telling you. And so going back to this picture that I looked at the 151 nodes because I had a memory that they were there, and they were in the 151 nodes. But those are those planes. And so this is what they look like. We drew them the other day that the S is a sphere, that a p orbital is the infinity sign. And so it's not that the electron is following this path, it's that it's a pulse that looks like that, because it can never go through the center because that's the nucleus. So it's just a pulsing that ends up looking like this, pretty much mostly out here, or it's a probability of a pulse. And the D's look like the 4-leaf clovers. And that's where they get interesting, because the one of them has like a little donut in the middle, but it's the number of nodes. All right. The other thing is 0, 1, 2, 3 is it also, as you increase the L number, you increase the energy. So this is actually important because electrons want to be at the lowest energy possible. And it's the N plus the L number that tells you the energy. So if you're asked to compare energy, there's going to be a trick to do it with the periodic table once I show you that pattern. But the other way is the N plus the L number is used to determine the order the electrons fill in or occupy orbitals. That's just kind of a side note. And we may run into it today or on the study set that you can always go back to that trick, because it is actually a numerical thing. The other thing, going back a step, the N, right, the N, L is always less than N. So L can be anything from 0 to N minus 1. And so what that means is when N equals 1, you can only have L equal to 0, which means you have the 1s is the only thing possible. So on the first floor of our apartment, that first level, that's the closest in, the only possibility is a sphere. And the reason for that is you don't have enough energy yet in that first level to do these more complicated patterns. Because the pattern of the orbital starts getting more and more and more complex. Like we had a 6H. What the heck does a 6H even look like? That would be pretty cool to Google. So if N equals 2, then we can have a 2s or a 2p. And so once we get to the second level, we have enough that we can have these p orbitals, but we don't have enough energy to do a d. When N equals 3, we can have a 3s or a 3p or a 3d. Now the 3d has more energy than the 3s. So the more complex it is within a layer, as you also increase the layers, they have more energy, and so on. All right, and then the ML, that was also from our study sets today, that the orbitals are the path of the electron. And so that's this shape or the pulse that it's following. And again, this can be anything from negative L to positive L. So for the MLs. And that's where we then get this other piece up here that for SPDF, there's 1, 3, 5, or 7 possible orbitals. So SPDF is the subshell. And the 1, 3, 5, 7 is the number of ML possible, which is the number of orbitals. It's another way of thinking of it is for P, there's 3 possibilities, and that would coordinate with the 3 dimensions that we think of, that there's the x-axis, the y-axis, and the z-axis. So your infinity sign could be along the x-axis, the y-axis, or the z-axis. All right, I have to take this off because it's... And we're going to add one more piece today that we did not have in Schrodinger's original formula, his original equation. He did not talk about electron spin. This was added by, I think, Paul Dirac had added this piece to it. And so it's given MS, so the S is the spin. And this is the really cool one. So I sat through a year of physics, 8 years ago, 9 years ago, because of this question. Yeah, it was in the 7th week of the 3rd term that it was answered. And I'll tell you what the answer is in a minute, but electrons cannot have all 4 quantum numbers the same. And so 2 electrons can be in the exact same orbital, in the exact same space and time, as long as they're spinning opposite. So, and when we're talking about opposite spins, we're not talking about like running around the circle. We're talking about on its axes. So electrons are considered like itty bitty little balls, like little marbles that we would never be able to see. So think of it like a basketball. If I had a basketball in class, I usually have a basketball, and I can't do it. I can't spin the basketball on my finger, but you could spin the basketball clockwise or you could spin it counterclockwise. And so you can have opposite spins. So they can be in the same orbital. They can both be in, you can have 2 electrons in the 1s orbital. They do not collide into each other as long as they have opposite spins. And so I'm always asked, how is that possible? And I said, I don't know. That's just how that's what the law is. It's actually a law. It has to do with electrons are a charged particle that is moving, which means they have a magnetic moment, and it's laws of magnetism. It's designated MS, can either be a +1/2 or -1/2. Those are the only 2. They gave them a half number to differentiate them from Schrodinger's original 3, which talks about orbitals and stuff, but that you can have any orbital, not subshell, any orbital can have maximum 2 electrons. So 2 electrons max is what this is going with. So this would be if I like got 2 electrons. Yeah, it's pretty crazy. They don't collide into each other. So when I sat through the physics class, this came up, and I made the mistake of sitting in the middle towards the front. And somebody asked the question, the answer that Dave Faust, who's like brilliant and amazing teacher, take physics at Mount Hood, he's amazing, just looked at them and said, well, it's a law. It's a law of magnetism. And everybody went, oh, and jotted it down. And I'm just sitting there going, you get to answer questions like that when you teach physics. You just say it's a law of Newton, it's a law of this, and everybody's like, okay. Basically, a law means we don't understand enough yet to explain the math behind it, but mathematically this holds true, and so we go with it. And so that's his name is. And so it is given the name Pauli exclusion theory, and I don't fully know why, but it's the maximum occupancy of any orbital. So with that, though, if you're in a p orbital, you can only have 2 electrons, but if you're in the p subshell has 3 orbitals, and each orbital holds 2 electrons. So we're going to see the p subshell can have 6 electrons in it. It could have 1, it could have 3, it could have 6. So that's what this question is here. So maximum electrons in the 3D subshell. So 3D is 5 orbitals, and that's back up here, right? D has 5 orbitals times 2 electrons per orbital, so 10 electrons can occupy the subshell. However, in a 3D orbital, as soon as it specifies orbital, it's 2 electrons. So just be careful of the wording. The word shell versus subshell versus orbital means something different. If we're in the 3rd energy level, that means n equals 3. So if we take 3 squared, we get 9, and 9 tells us that 9 means what? Like students get, yeah, I just take 3 squared because all she gave me was the n number. What does the 9 tell me?
The maximum.
The
Is it
number,
the number of possible orbitals?
it is. Was that max? I don't know who said that.
That was Max.
Okay. So 9 times 2 electrons would be 18. So yeah, so when you do that n squared, if the only thing you're given is the n number, you square it and it gives you the number of orbitals. So questions with anything from that page, or do I need to move that? All right. So I think we get to the fun. Yeah. Here we go. Page 60. All right. So I'm going to pause for 5 minutes. I'm going to give you a chance to see what you can do. So like on the first one, right, you're looking to see if it's legit. For the MS, you can see right off, that's the only one that's not going to be possible. And then down here, you want to figure out how many orbitals, and then you double it for the electrons. So I'm going to pause this. And again. All right. So, and also, I want to mention my headphones do something wonky again. Please let me know. And I will, it's quiet. Last time it was really noisy in my house, and so they muffle out the noise so I can focus. But
Sorry, I
no,
know.
but
I was trying to rewatch the lecture on the YouTube.
I know on Tuesday something was weird with him.
Yeah, like the blinking.
Yeah, I don't know what was going on.
My screen, then I just figured it was only happening on the YouTube.
No, I think it was something happened by Tuesday morning. Well, Tuesday morning, actually, the Wi-Fi went off, or the internet went off, my whole area. So I was in the middle of my lecture, and all of a sudden, everybody disappeared, and I was like, "Where'd everybody go?" And then I realized I'm like, "Oh, my Wi-Fi, everything went down." And so it took like 10 minutes before it came back on. I go back, and the whole class is there waiting for me. They're just like doing other stuff, and they're like, they knew I'd come back. And the one guy said he got kicked off too, and we found out he lives like a mile from me. But all right. So which possible or not? First one looks good. So we're looking for, like on B, you can't have a negative L. So that's, L can't be less than 0. That's not possible. C looks okay. So we'll come back to that one. And then D, the MS is only can be equal to positive or negative 1/2. So this is no good. So we ruled out B and D. Now we have to go back to A and C. So the ones that are good, you then go back and just look at the first 2 quantum numbers, the N and the L, and you say your little thing, SPDF. And this time we're doing the 1, 2, 0, 1, 2, 3. So the L number tells you which one. So this is a 4p. This is a 3d. So questions with that? So you're going to see that question on your study set. I will open the folder up for next week. It's just going to have MS numbers now. And I think I ask you, be careful if I ask you orbitals or electrons. I usually ask both, and so we're going to actually do both. So if you have the N number, you just square it, and that 9 is the orbitals. And to find the electrons, you just multiply by 2. So 18 electrons max. It doesn't mean there's 18. It just means at the 3rd floor, at the 3rd shell level, you can only have 18 electrons. All right. If you have the L number, that's specifying that this is the 4p. And so 1357, sorry, that is the number of orbitals. So if L equals 1, it's a p orbital, and so it's a p subshell, so there's 3 orbitals. Times 2 is 6 electrons max. Our next one.
I'm sorry, for the first one, you said the n squared would be 9, and the 2, is it the L?
No, the 2 is just whenever you go from orbitals to electrons, 2 is the maximum occupancy. So you always double it to figure out the number of electrons. So that's why, like here, I double it. It goes back to this. The maximum occupancy is 2. Is that
Okay, yeah,
Yeah.
that makes, okay, that makes sense.
so? And that's what the MS, positive or negative 1/2. That's the 2 possible. Always look first to make sure it's possible, because if it's not, we get a 0. I think we do run into that. All right. If it gives you the ML, so if the ML is given, that is a specific orbital. So this is 1 orbital because of the ML. So there's only going to be 2 electrons, one spinning clockwise and one spinning counterclockwise. So if I was like really played with the Harlem Globetrotters and could spin a basketball in 2 different directions, it would be that you could line the basketballs up and they would be on the same finger spinning in opposite directions if they were electrons, because electrons have a charge, which means if they're spinning, they have a magnetic moment and they can both exist at the same place as long as they're spinning opposite and they don't collide. Really cool to ponder. There you go. You meditate on that for a week. All right, on the next one, we want to make sure all our numbers are good. So L is less than N, the ML is between there, and the MS is plus or minus 1/2. And I do, sometimes I put the plus and sometimes I don't. That's just, I don't know why I do that. This is specifying the electron. That specifies the electron. So the answer is only 1. Once you're given the spin, you're told which electron in the orbital. So for those of you who've done this is where we're going in the next 10 minutes. This is the up and down arrow is the spins. So I'm now specifying which one of the arrows. So it's a specific electron. The orbitals are the lines that we're going to get to. All right, the next one, the answer is what on E?
Is it impossible?
It is not possible, so none. Why is it not possible?
So the MS is 2, and it could be either
Or
positive.
the ML, yeah. So because of the L, if L equals 1, then ML can only be -1, 0, or 1. And so that's the boo-hoo part. So you always want to make sure that you have a group that works. All right, so there we go. Those numbers are good. And so it gives us the ML. So this is again a specific orbital. So it's 1 orbital, and the orbital can have 2 electrons spinning opposite. So 2 electrons was our answer. The next one, I'm specifying the subshell. So you can go back up here. D means 5 orbitals, which you're all going to know, hopefully. Well, this is what we're going to put it all to the periodic table in a moment. Times 2, so 10 electrons is our answer. So questions with that? All right. I actually took this right from the study set and then just changed some of the numbers around. So hopefully when you do, go ahead.
Could you talk about number D?
This one?
Yeah.
What about it?
How did you get 1?
Because the MS is given, the spin is given. If the spin's given, it's telling you which of the 2 electrons. So if this one has 2, it's because there's 2 MS possibles, positive 1/2 and negative 1/2. If you're given the MS, you're told which electron it is.
Okay, what if could it be a -1/2?
It could have been.
And that would still be 1 electron?
Yes.
Okay.
All right. Which of these are impossible? The other term is improbable. Yeah, or not possible. So 3p is good. 2d is no good. So when n equals 2, L can only equal 0 or 1, which is S and P. So the 2D is the one that is no good. 5F and 6G, they are possible. They're not on our periodic table. We're going to talk about the periodic table in a moment, but they can happen. When n equals, like if we go to 6, if n equals 6, then L can be 0, 1, 2, 3, 4, or 5, which is S, P, D, F, G, and H. So 6G is possible. It would be a really huge amount of energy because G paths would be pretty amazing. All right, so go for it. You need a periodic table. And if you watch that pre-lecture, this page is blank because we're gonna write a lot on this page. You're probably gonna need more pages. Pretty sure you will need more pages. I do this experiment in that video in case it's always fun. I actually had meant to give you a page with a periodic table on it. So we're gonna put all that theory to practice with one other rule. He's probably a chemist, so he only gets to make rules. And the rule is that you always go with the lowest, the ground state configuration. They're called electron configurations. I don't know why. That's what we call them. And that just means we always go from lowest. You start with the lowest energy possible, which means, sorry, you're going to always start at 1, at n equals 1. So we're going to start at n equals 1, or the 1s. So we'll start with hydrogen. And hydrogen has it's element number 1, and so it has 1 electron. And so hydrogen, actually, you know what? Let's do it with this one first. So hydrogen we're going to always start with the 1s. And so I teach you the shortcut because we're going to get to gold tonight, as I always promise. And we would put that electron there. So this is called NLX. It has several different names, and I don't remember any of the names anymore because there's so many. But you're going to be taking stuff from me, which is your study sets and stuff. So NLX means the shell, right? N. The L means the subshell. So that's what we've been doing, 4D, 6H, 1S. And then the X is the number of electrons. And that X is a superscript. So for hydrogen, there's 1 electron, and we put that electron in the lowest energy possible. If we go to the next one, to helium, and I will start skipping around, we would say 1s2. So we now put 2 electrons in there. So when we get to lithium, lithium is number 3. We can't put 3 electrons in the 1s. Why can we not put 3 electrons?
Only 2 electrons per
Back
orbital.
to that Pauli exclusion theory, or what Dirac came up with, that you can only have a spin, positive or negative. So you can only have 2 electrons in the S. So then we go to the next one, which is the 2s, and we put 1 electron there. And that's my screen. Right. All right. Let's skip to boron. Why not? So boron is number 5. So we start with the 1. We fill up the 1s, and then we fill up the 2s. And hopefully you didn't rush ahead. We don't go to the 3s, because if you remember, there is a 2p. So when n equals 1, we only have one possible, there's only L equals 0, so we only have the one S. When N equals 2, we have 2S and the 2P. When N equals 3, right, so on. And we're going to walk through this today, so you'll see the pattern, and then hopefully when you go back to do your study set, it will help it flow in. And for those of you who this should be looking familiar, this ends up being most students one of their favorite things we do the whole year. Let's jump. Oh, and that would have one electron. All right, we're going to add another piece to this. So that's NLX. So before we move on, oh, actually, yeah, let's do nitrogen. I never do nitrogen. So 1s2, 2s2, and you would actually go to 2p3. So how comes I can suddenly put 3 electrons in the 2p? Damon just answered, I can't crunch 3 into the 1s, can't crunch 3 into the 2s, but why did the 2p suddenly get a 3? Well,
You can have up to, in the P's, you can have up to 3 possible orbitals.
yeah, so SPDF, remember this little thing? put it as a flashcard, put it up there with your periodic table on your wall, 1357. That's the number of orbitals. And each orbital you times by 2 electrons. So P can go up to 6 electrons. So we can get up to 6 here. We're going to add another part to this. And so that's the NLX, where we say where they are. In fact, we can go to 6. Let's go to 6 with neon. So neon would be 1s2, 2s2, and this 10 is the atomic number for neon. So if you have your periodic table, that 10 is right there. And for those of you who this is new, you're going to get it. There's a pattern, and we just have to get there. So it's kind of follow along, and then it suddenly clicks. So you're adding up these numbers, the superscripts, the 2 plus 2 plus 6, that gets me the 10. So I have 2 electrons here, I have 2 electrons here, and then I have 6 electrons there, and I have the 10 electrons. Neon is element number 10 because it has 10 protons, 10 electrons. Back to our very first lecture. All right, the other way we're going to designate these is called box, this is what your teacher calls it, box and arrows. They're really going to be lines. I'll show you with the boxes because you'll see them online some places as boxes. The boxes are the orbital. And the arrows are the electron spin. So the arrows are going to either be an up arrow or a down arrow. You don't go sideways. So you can either spin up or spin down. It's designated clockwise or counterclockwise. That doesn't matter. It doesn't matter what direction it's spinning. It's just if they're in the same orbital, they spin opposite. So if you like to do boxes, you make a box. So S has 1 box. So the number of orbitals is going to be our number of boxes or line. And then we show our electron spinning. So there's our electron spin. If you want to just do lines like your teacher is going to do, you just put a line instead of a box. And now when you have 2 electrons, 1 spins up and 1 spins down. I do half arrows because that's what most chemists and physicists will designate them as. You can also do a full arrow. That's not a big deal. It's just an efficiency thing. All right. So like on this one, we would have, here's our 1s has 2 electrons, and then our 2s just has 1 electron. If there's only 1 electron, you have a choice because the electron has a choice. It can spin clockwise or it can spin counterclockwise. It doesn't matter. It will matter eventually. All right. So for boron, that's my 1s, has 2 electrons. There's my 2s. It has 2 electrons. Now, when you get to the p has 3 orbitals. That means you have to show 3 lines. You have to show all 3 lines. Once you open the subshell, you have to show everything that is possible. And you have to bracket those lines to show those 3 go together. They are equal in every way except their orientation in space. So they have the same energy. And so this is an electron. This is like Damon was talking about his little house. Damon moves into a bigger house and he now has 3 rooms. And he has his choice of which room he wants to sleep in. Doesn't matter. You have 3 rooms and you can sleep with your head up or your head down. You can do a headstand all night. And so you can put that electron anywhere you want. It is going to matter on nitrogen. All right. I'm going to do this one with boxes just to show you what boxes would look like. And there's always somebody who likes the boxes. So you show your arrow. That's our 1s. The 2s is a separate box. It has 2 arrows. And then you do like a long rectangle because it's a bigger apartment. It's a 3-bedroom apartment. And so you do 1 long rectangle and you split it into 3. When we get to the D's, we do a longer rectangle and split it into 5. I just do lines and bracket them together. So there is a rule. And it is, I think it's actually part of Hund's rule. When you have more than 1 electron in a subshell and there's multiple orbitals, each orbital only gets 1 electron before they pair up. Electrons are negatively charged. They don't want to pair unless they have to. So if they don't have to pair, they don't. But there's more. They all spin the same way. That is a law of magnetism. All of those electrons have exactly the same energy, exactly. And so they have to all spin the same way in the 3 separate orbitals before they start pairing up. So all 3 of them are going to spin clockwise or counterclockwise. That doesn't matter, but they're separate. They don't share a room. They're not like 3-year-olds who all want to be in the same room. They are like teenagers who all want their space. All right. So when we get to neon, should pick somebody different. That's all right. We'll do more. Just bracket them. You can do your brackets however you like. Just have to show those 3 go together. And this is going to have 6 electrons. Neon is special. What family is neon in?
Noble gas.
It is a noble gas. Noble gases are called noble gases because they do not react. They did not discover them when Mendeleev did his original periodic table. If you go back and look at it, there's no noble gases. They didn't know about them yet. And when they found them, they don't react. And they don't react because their electron configuration is perfect. They're all full. Nitrogen reacts. It has 3 empty spots there. Hydrogen reacts. Anything with empty spaces is going to react to either get rid of that or to fill it in, just depending where it is. So like lithium tries to get rid of this one. Nitrogen tries to fill those in. And so that goes back to all the cation, anion stuff that we talked about. All right, so let's keep going. I'm going to teach you a shortcut. So let's move on to sodium. So sodium's number 11. And so you can watch what I do or you can write this down. You can do 1s2, 2s2, 2p6. That gives us 10 electrons. That is neon. Or you can just write neon. You can only do this for a noble gas. Neon is perfect. And then you write what's after it, which would now we go to the 3s because the 2 is full. So this is how you're going to see me doing them from here on out. is I just showed this. The neon part are called core electrons. They don't react. And so it's not just an efficiency thing that we do this. We do this because this 3s1 is called valence electrons. That reacts. It's going to react either to gain, lose, or share electrons in a chemical reaction, that electron. And that's called a valence electron, and so there's one of them. So the other thing that's nice about the shortcut, all you have to do is show that one orbital for the 3s, and you're good. So in the shortcut, you can only start with a noble gas. You can either start at the beginning, or you can start with a noble gas. So I'll show you more of how it all fits together in a moment, but let's do a couple more here, which is, skip to silicon. So silicon is number 14. So we're going to start with neon. And I'm going to show you in a moment how you know which noble gas to start with, but we're going to start with neon. And neon is element number 10. So I'm going to write the 10 there today to help us. So silicon is here. We're going to start with neon. You can only move forward. So you have to start with the noble gas that came before the element. So neon comes before silicon. You can't go backwards on the periodic table. So you can't start with argon and say, hey, let's take a couple away, because argon's perfect. It's not going to want to take some away. So we're going to start with neon, and it says we have 10. And then how do I know I go to the 3s after that? Well, there's a whole pattern to the periodic table. And this is a point in class where everybody usually has the same periodic table, but I would tell you to number your periodic table down 1, 2, 3, 4, 5, 6 as the rows. And the periodic table is actually in a pattern. And we're going to write it on this one. So this is 1, 2, 3, 4, 5, 6, 7. So we're trying to do silicon right here. So how to know where to start is you start with the noble gas that came before it, which is neon. And then after neon, neon's number 10, you come to number 11, and it's going to tell you I'm in the third row now, and that is the number you start with. You say I'm in the third row, and you always start at the S's. So if we started with Krypton, well, after Krypton, we'd come down to rubidium, and you would say, okay, I'm in the 5 row, the 5 S's. We're going to do enough of these. We got time. All right, so we're going to put 2. We need to get to 14. I'm at 10. So I put 2 in the 3s, and then I'm going to put 2 in the 3p, because 2 plus 2 plus 10 is 14. There's more to the pattern. I'll get to that. So I draw my 3s. I draw all my p's. And what happens now? Where do those 2 electrons go? They have a choice, but only some choices. So really the question I should ask is, where do they not go?
Together.
They do not go together. So they cannot pair up. So they will go in different orbitals. They can go into any 2 orbitals. When they go into that orbital, as soon as one spins one way, the other one has to spin the same way. So when you're filling in the p orbitals, the first 3 electrons all spin the same direction before they start pairing up. So how many valence electrons are there? It's a really simple question. It's everything after the neon. So 4. How many unpaired electrons? So unpaired is the arrows. It's not how many empty spaces. That's not what we're asking. How many unpaired electrons? So there's 2 arrows that do not have a pair. So 2. Then there's one more question I always ask, which is the HEO. Does anybody remember what HEO stands for?
Is it highest
Electron.
energy?
Oh, yeah, energy.
It is highest energy.
Occupant. Occupancy.
Yeah, occupied orbital. Highest energy. Nobody says that. Everybody says HEO. I'll write it out in words too, but it will just say HEO. Highest energy occupied orbital. It's the last subshell that has electrons. Does not have to be full. It just has to have electrons. And so 2. You know what's really interesting? I just realized with my headset, when I taught quantum last term, the same thing happened with my headset. It was like whenever I'm teaching that, apparently all my electronics must know it. When you first learn Qigong meditation, that my teacher from China actually told us that we couldn't do it like around electronics and stuff. And anyway, because weird stuff happens, but go figure. Let's do sulfur. So sulfur is number 16. So you're going to start with neon. So here's sulfur, noble gas that comes before it. Eventually you don't, it's up to you. You don't have to write the 10 there, but it's really nice when you're first learning to make sure you got the number. But once you see the pattern, a lot of people stop writing the 10. We're going to get to the pattern soon. So 3s2 and then 3p4. Because 2 plus 4 is 6 plus 10 gets us to 16. So there's my 3s. Here's my 3p. Bracket it however you like. The 4 electrons. 1, 2, 3. Each one gets 1, going the same way. You can spin them all down if you want first. It kind of depends on your mood. I always spin them up first, which you would figure. And then one of them pairs up. So that's what it looks like. So valence electrons, let's go ahead and go through this. Valence electrons is 6. Everything after the noble gas. So anything after the noble gas is valence. Unpaired is 2. So again, it's not empty spots. It's what arrows don't have a partner. So we had 2 here and we have 2 here. And then the HEO. Oh, you know what? I don't know why I wrote 2 there. It's 3p. I don't know what I said and why I wrote 2, but on the previous one it was 3p. So it's the designation. I apologize. 3p. So the HEO is the highest occupied orbitals. They don't have to be full. They just have to have an occupancy. So sulfur and silicon are both 3p. All right, let's jump to, is it calcium? Yeah, let's jump to calcium. So if we jump to calcium, calcium is number 20. And the noble gas that comes before calcium, calcium's number 20, would be argon. So we're just going to say argon. And then, oh, this is numbered 2. So after number 18, we come to 19. One of the things, and I usually mention this, that we made the periodic table flat, like when we make a map of the world, we flatten it, which is incorrect. The periodic table is a spiral. So chlorine is right next door to argon. Potassium is right next door to argon. You can't look at it like it's a flat map, like we're in Oregon or New Jersey. It's right next door to it. So we come down here, and this person kindly labeled already, instead of just numbering 1, 2, 3, 4, 5, 6, they actually wrote 1s, 2s, 3s, 4s. So we're in the 4s. So we would say argon, and then we're in the 4s. And I want 2 electrons. And I know I need 2 because argon was 18 plus 2 more. And that's what we would have. So let's answer our questions. How many valence electrons? 2. How many unpaired? 0. Yeah, when there's 0 unpaired, that makes them actually very stable. The earth metals are actually very stable. And then the HEO is the 4s. So questions up to that point, because now the fun begins. But that's the basic idea. Because there's a blip that happened that everybody trusts me. And if we wrote out argon, you don't have to do this, you can just listen, is 1s2, 2s2, 2p6, 3s2, 3p6. That gives me argon. That would be argon. And then I suddenly jump to the 4s. And the reason I'm asking this question is when n equals 3, what happens to the 3d? I left it out. And it has to do with 2 things determine the energy of that orbital, the n number and the L number. So let's do the math. So 4s, that would be L is 0, so this would be 4 plus 0. And the 3d, that would be 3 plus 2. That's higher. That has more energy to it. And so that was part of his math, part of his whole equation. And it turns out it's perfect for the periodic table. But back to the question that many of you pondered when I first taught this piece. It's like, why do the D's do that? The D's have, I'm looking for my picture. All right, the D's have a lot of energy. So the D's were that 4-leaf clover. And that pattern of a pulsing energy is very complex and knocks them up higher energy. So the pattern on the periodic table is these first 2 rows on the periodic table, these first two columns. The rows are 1, 2, 3, 4, 5, 6, 7, but these first 2 columns are called the S block. And so this is the 1s, the 2s, the 3s, the 4s, the 5s, 6, 7. Over here, there are 6, starting with boron to neon, and this is the P area, the periodic table. And they also correspond to the rows. So this was 1s, 2s, 3s, 4s, 5s, 6s, 7s. Over here, we have the 2p, 3p, 4p, 5p, 6p, 7p. So Orgasian, I don't know what it is, Orgasian, yeah, is the 7p's are full. The middle here, the transition elements are the D block. And the thing about the D block, because the pattern of the D orbitals is so complex, they always knock up a whole row. So the 3 Ds are in the 4th row. So at scandium, maybe better on this one, at scandium is where we start the 3 Ds. The 3 Ds are going to go from scandium to zinc. Starting with deuterium to cadmium is the 4 Ds. Let's go back to this. If I use the green pen. So 3 Ds, not really. 4 Ds, 5 Ds. These down here are the Fs, and they are the 4 Fs and the 5 Fs. Now, interestingly, on my bike ride today, I was biking and I saw one of my colleagues, guy who teaches in the PE department, out mowing his lawn. So I stopped to talk to him, and then suddenly a truck drove by and they stopped. And they're like, "Are you Dr. Joyce Sherpa?" Because I'm dressed all in pink on my bike so nobody hits me. It works. And it was one of my students from 5 years ago, and we were talking about stuff. And I was saying, what's going to happen when COVID's over and you guys all go back to classes? You can use Google to give you all the answers, but at some point you're going to go back into class, and maybe you're not going to have to draw electron configurations, but having this understanding. So don't rely on just Googling everything to give answers. I can tell who uses Google because the answers are always a little wacky. Kind of pretend like it's the real thing. And so this is the 3Ds, the 4Ds, and try and do it without Google and using your own brain cells. It's really good for your brain cells, actually. And again, down here is the 4Fs and the 5Fs. The Gs, we're just getting there, and they're changing the periodic table. So how this is going to work, we're going to do vanadium. So vanadium is number 23. And while I'm thinking about your innovation papers, it's all similar as last time in your presentations. If you don't like your innovation, just send me an email. 2 people actually did today, so you won't be alone. We can change up through Tuesday, no problem. Even Wednesday, I've had people. So if you're not finding stuff or it's not quite what you thought, you can absolutely change it. All right, vanadium's number 23. On our periodic table, the noble gas that comes before it is argon. So we're going to start there. And argon is number 18. And after argon, here at 18, we come down to number 19, and it's going to be the 4th row. And how we're going to be writing it is we're going to say it's the 4s. And we put 2 electrons in it because it's S. Goes back to SPDF 1357. All right. And then this is where having the understanding of the pattern on your periodic table, that after the 4s, when you're here in the middle, you're in the Ds, and it goes from 4s to 3Ds. The S's and P's are going to always go with the row number. So 4s, 3D, and then we're back in the 4Ps. So 3Ds come next. We are showing from the lowest energy to the highest energy. To get full credit when you show these, you have to show it this way. Google shows it a different way. And I can explain that way, but we're going to show how they're filling in. The 4s comes first, and then the 3D, and you can count over 1, 2, 3. So 3 electrons must be in the 3D. That gives me 18 plus 2 is 20, plus 3 more is 23. How we do the box and arrows. That's my 4s, so 1 line. So this is the number of lines or the number of orbitals. And for D, I'm going to do 5 lines, 1, 2, 3, 4, 5. You're going to bracket them somehow, show those 5 go together. If you don't bracket them, you're not going to get full credit. So just putting a random number of lines and hoping I don't count. Even if you have the right number of lines, you have to show those go together. So these 3 electrons cannot be paired up. They each go in a separate orbital. It doesn't matter which 3 orbitals you put them in, but they have to be in different orbitals, and they spin the same way. Again, it's a law of magnetism. Since they're a negatively charged particle that is spinning, they have a magnetic moment. Let's do germanium. And then I'm going to give you a couple to try, and then we'll look at, yeah, that should be good. Oh, sorry, that doesn't go in the brackets. What noble gas would we start at for germanium? So germanium is here, number 32. Again, you cannot start at 36. You cannot go backwards. So you have to go to the previous noble gas. So you're going to start at argon. And after argon was the 4s. So again, argon is number 18. You come to 19. S's hold 2. And then we go through the Ds. You can count, but if you're past zinc, then the 3 Ds are full. And since Ds have 5 orbitals and every orbital has 2 electrons, it's going to have 10 electrons. And then, so that's scandium to zinc. The P's start here. So it's straight blocks. I have a picture of it. I have to find it while you're doing practice. So gallium and germanium, that's the 4 P's. So we're back to the 4s. So 4p, and we put 2. So 18 plus 2 is 20, 30, 32, and germanium was 32. So box and arrows, that's my 4s. I'm going to label them, just make sure. My Ds, they're going to be completely full. So there's 5 lines and 10 electrons. And then my Ps, 3 lines again. Those two arrows do not pair up. So if I ask you valence electrons, unpaired electrons, and the HEO, valence electrons, this is going to be 14. Everything after our noble gas. So there's 14. Unpaired, only those 2. So we had 2. And the HEO is the last that has any electrons. So that would be my 4p. In fact, once you get this, you can answer the HEO without drawing this. You can do all of these questions without drawing the orbitals. On your study set, I think there's only 3 that you have to draw the orbitals. You can always draw them to figure it out. But once you see the pattern on here, if I asked you, what's the HEO in phosphorus? Okay, phosphorus, it's in the P block. It's over on this side, and it's in the 3rd row. So phosphorus must be a 3p. If I asked what's the HEO in bismuth, well, P block and 6th row, so it's a 6p. If I asked for silver, first of all, you have to know that silver is Ag, and it is in the 5th row, but it's in the D block, so it's the 4 Ds, because the Ds are always 1 off. You can ponder that. You'll see these questions in your study set. So I'm going to give you a couple to try, and I'll do a pause then. Let's do molybdenum. So MO. Let's do iodine. No, tellurium. Maybe. Oh, I keep writing the wrong letter. All right, we'll just do tellurium 52. And then I promised we would do gold, number 79. So you're doing both box and arrows, the NLX and box and arrows. Do the shortcut. And then you're going to tell me valence, unpaired, and HEO. So I'm going to pause us and give you a couple minutes to try it, or you take a break. You can ponder. Then. So Major asked a question during that pause about the Fs. I am not going to ask you to do electron orbitals in the Fs. Something I would ask you about the Fs is how many electrons or how many orbitals does an F subshell have? And you would say, okay, an F has 7 orbitals, or it holds 14 electrons. Or if I asked, is that erbium, I think? What's erbium's HEO? That you find erbium, I think that's that. And that's the 4 Fs. So these are the 4 Fs and 5 Fs. The issue is that the 4 Fs and the 5 Ds are really close. So if you add the n plus the L number, so this would be 4 plus 3, and this would be 5 plus 2. They both come out as lucky number 7. Same with the 6s. Sorry, not the 6s, the 6p. The 6p would be 6 plus 1. So they're all coming out at the number 7. So the next one would actually be the 7s. So the order, if you come out with your n plus L number is the same, it means their energy is pretty close, but the lower one is the one with the lower n number. You fill that first, and then you start filling the next one. But something I was saying to him during the break is as you start adding electrons, it does change. It does actually make it more and more stable, so it actually lowers it a little bit more. But on the periodic table that I usually use, it appears that that first electron actually goes into the 5D before it goes into the 4Fs. And they keep changing that because of stuff that goes on at CERN. And does it really matter? I don't know if it does or not. It probably allows cool things. These guys down here in the 4Fs, these are like the really expensive headphones. This is also why my headphones did weird stuff, because electrons start jumping funky. But let's go back to this. So molybdenum is number 42. And so we would start with Krypton. And Krypton is number 36. Again, you don't have to put that number, but it's helpful to see if you got it right. And then after Krypton, so 36, we come down to 37. So the rub-a-dub-dub 5s, 2. S's are always going to have 2. And then we're here, and this is, if we're in the 5th row, we go to the 4D. So 4D, we'd go 1, 2, 3, 4. So starting with deuterium, zirconium, niobium, molybdenum. And then we show our order. 2, 1, 2, 3, 4, 5, bracket them. These 4 just all spin the same way in separate orbitals, any 4 orbitals you want. So 6 valence, 4 unpaired, and 4D is the HEO. So I want to show you something with this one. If you ask Google, it will give you a different answer than me. And so one of the things that Google will do, and they are correct, and I don't usually teach this, but I mention it, and especially in this environment, I need to. It happens with chromium's family. So chromium, molybdenum, and tungsten. When there is this one empty, I made a comment, there are 2 stable places on the periodic table. The stability of having a completely filled subshell, that's huge. That's like super stable. So the noble gases, there is also a stability if they all have unpaired. And so what happens when you get to chromium is it actually stills an electron, or it's molybdenum, so chromium, molybdenum, tungsten, and seaborgium. And so actually, this one becomes an unpaired, and you get an unpaired there. You actually end up with this, and you actually end up with 6 unpaired. So I usually don't ask that kind of a question, like on a celebration. I'm mentioning it though, because it does happen. It's also like with chromium, it's part of chromium's issues that chromium, that family is called the 6s because they could do a +6 charge. And it turns out it's because of this. And again, this is all theory. There's no way we can know for sure if that happens, but it appears that it does with that family. But all unpaired actually is a place of stability. It only happens with Ds. Ps never do anything like that. Ds sometimes do something funky. All right, Te. So telluriums over here, we would start with Krypton. And then we do 5s, we go all the way through the 4Ds. So after Krypton, you're here. These are the 5S's, all the way through the 4Ds, and then we're back in the 5Ps. So your S's and P's are going to be the same number. And then you count 1, 2, 3, 4. So 1, 2, 3, 4. You can check your math. And so we have 16 and 36, so you get 52. Dr. Russell actually did his doctorate in something to do with the transition elements, and he has a really funky name for them. It's really funny, and then I can never remember it. But I don't know much about the chemistry of them because I'm actually a biochemist. All right. Other than they do really weird stuff. So P's only have 3 orbitals, 3 lines, and then 1, 2, 3, 4. So valence is all of these. So the valence is electrons is 16. Unpaired is only 2. And the HEO is the last one, the 5P. Now, I also wanted to show how Google would show this one and all of them. We're going to be showing it from lowest to highest energy. It would show Tellurium as Krypton, and then it would show 4D, 5S, 5P. I don't know who came up with this way, and I think it came from this weird thing that goes on with the 4Fs to get around it. But what they're showing is from the inside to the outside, which is interesting, but that's how it would be. All right. So gold. To do gold, we're down here. We would start with xenon. Xenon's number 54. And then we will be in the 6th row. So 6S, 5D, 6P. Oops, you don't have to do that. I'm sorry. Forgot what I was doing. I thought I was doing lead for a second. So 5D9. And the problem is, it's a question that Major had asked me. He didn't realize he asked this, but if you add this up, 54 plus 11, you only get 65. We're missing 14 electrons, and that's because of this gap right here. That before you fill the 5Ds, the 4Fs are there. They put it down below on the periodic table, one, because these are very rare. They're not common at all, but it wouldn't fit. It would make the periodic table super long, and it wouldn't fit on our piece of paper. But the 4Fs actually squeeze in there, and there's 14 of them. And so it would be more if we had one that was in the 5Ds or 6Ps. You go 6S, then the 4Fs, then the 5Ds. You show the 4Fs before the 5Ds because of that rule of the N plus the L number. If they come out the same, the lower N goes first. The 6S goes first because it's the lowest energy. Again, on Google, they would show 4F, 5D, 6S, but that's not showing as something very useful. I also wanted to mention, so you could do your box and arrows. Gold's family, and it is only Gold's family that does this, does that thing. They actually always steal one. So you would get full credit for this, but because many of you are going to Google it, this one actually loses one and it comes over here. So it actually comes out as 6S1, 4F14, 5D10. It's only the Ds that do this, that if they're really close to being full, it's like, I want that one. Mendeleev's original periodic table actually put copper, silver, and gold, they didn't even know about electrons yet, in this family with the 1As, which is actually quite fascinating because they behave like them. So we're going to do one more piece here because I know it shows up, is if you have a negative charge, right? Negative means it's an anion or an anion. Remember that? Way back 2 months ago? Holy moly, you guys have come a long way. So kind of think about that. Ponder how far you've come this term and how much you've learned. We get caught up in doing the math and stuff, but it's like, yeah, I can talk chemistry. Like when she's saying silicon and pointing to things, I can find things on my periodic table. This means that they gain electrons. So of my examples, which ones would make an anion? From the first midterm. You had to predict anions and cations. Well, the anions are the nonmetals. So tellurium, we could give it a -2 because that's what it likes, or a 2 negative. And that makes sense. It has those 2 spots there. So if it had a 2 negative, you would fill in and you would now have no unpaired. It would come out just like xenon. It would be perfect. Now, if you get positive, so that's easy, negative. So cations lose electrons because cats become positive, right? Cats have pos, remember that? All right. So metals are cations. Remember we had dress up? Maybe I did. Daniela dressed up. So this is the weird part. When they become positive, let's do it up here with vanadium. So if vanadium became +2. When they become positive cations, they lose from the S's first, from the S subshell. It's just how it is. And that is because the S's are actually further from the nucleus. So this number, they lose the outer ones first, the most outer. And so it actually would lose those. Oops. And those. And you would be left with just argon 3d3. It's has to do with how far out it is. And so you could argue, well, maybe that's why they like showing it like this. I don't know fully why, but we're going to show them filling from the lowest to the highest. I think it actually has much more value and explanation. And again, too, so you have nothing due this weekend. Can you believe it? You have a worksheet due tonight. You need to start your 7-day quantum leap by this weekend. So look at that lab. You can do that lab. You can do the other parts of the lab so you have it done. So next weekend, when everything starts crunching in all your classes, you're going to have a study set due Monday. I'll open the folder, which is on this stuff. And our presentations are next Thursday. So namaste. I am going to stop recording.